So, hello everyone. Please be quiet. We are about to start. So, welcome everyone. Thank you for joining the last session before our lunch. So, our last session will be given by Ankur Ankan, a postdoc researcher from Radboud University. Please give some applause to Ankur. The floor is yours.
Yeah, thanks for the introduction. I'm Ankur, and I'm currently a postdoc, and I work mostly on causal discovery and causal identification. And this is also my first PyData, so I do not know the audience very well. So I just was wondering, like, how many people here do use causal inference or work with causal inference? Okay, not a lot, but okay. So I think everyone must have heard this phrase, correlation does not imply causation. And to show that, I took this very silly example where if you plot the distance between Neptune and Earth and burglaries in Kansas, you would see a pretty strong correlation. So if you look at the correlation coefficient, it's around 0.96. So if we wanted to build, for example, a predictive model to predict the distance between Neptune and Earth and use burglaries as our feature, we would be able to make a pretty good predictive model. But if we wanted to ask a causal question from this model, for example, like if we somehow reduce burglaries by, let's say, deploying more police, would that mean that it would also decrease the distance between Neptune and Earth? It's clearly no, but if we ask this question to a predictive model, it would say yes, definitely it would. So to put it a bit more concretely, so in predictive modeling, we are usually interested in predicting a bunch of outcome variables given some features that we have. And these methods usually rely on correlation between these variables. On the other hand, in causal modeling, we are more interested in identifying potential interventions. So for example, what would happen if we change something? So these what-if kind of questions. And methods here typically try to learn cause and effect relationship between the variables. And for that, usually just utilizing correlation information is not enough. So what we usually need for doing causal inference is some kind of understanding of the true data generating mechanism. So for example, here I've taken this example called causal protein signaling network. It's a model that has been verified experimentally. So the variables here basically represent our random variables that we have, and the edges represent the causal relationship between them. So for example, on the top, we see this protein called PKC. It has a direct cause on all of its children variables, for example, MEK, PK, RAF. So having a model like this allows us to have a mechanistic understanding of how our variables are interacting with each other. It also helps us in understanding how, given an intervention, how things would change. For example, in this case, we can think of like what happens to this mechanism when there's a new disease. Or it could also help us in identifying potential intervention spots. For example, if we somehow wanted to change the AKT protein at the bottom, we see that ERK and PK are like direct causal proteins to that, and we can somehow design an intervention for that. So the applications of these kinds of model are in many fields. For example, in machine learning, we can use these for interpretability or for feature selection, or making more robust model which can do out-of-distribution predictions. In epidemiology, we use it quite often for analyzing how different treatment and exposures affect health outcomes. And again, similarly in economics and social sciences for designing policy interventions. So mathematically speaking, there are two main frameworks where we do causal inference. So one is the potential outcomes framework, where we are usually interested in identifying or estimating the causal effect. So how much change in one variable would cause a change in another. So the estimation of this effect. And this framework mostly deals in providing robust statistical methods for doing this estimation. And some of the examples that you might have heard of are like propensity score-based methods or doubly robust estimators. And the second framework is this directed acyclic graphs, where we build these graphs. These graphs are at the core of the method. And from this graph, we can then try to estimate the effects that we are interested in. So if we look at the packages in Python, we have for both of these frameworks. So on the left, we have the potential outcomes framework with these mostly focus on specific estimation methods. So for example, do-I provides a collection of methods. The second one is double ML, which focuses mostly on this doubly robust estimation technique. Causal ML focuses mostly on meta-learners. On the DAG-based side, there's pgmpy, which I'll be talking about today, and then there's causal learn. So if we want to do a causal discovery, so trying to build that graph from data or to estimate any effect, this is usually our general workflow. So we start with some data, we do some kind of causal discovery algorithm on that, we get a causal graph. This graph, in most of the cases, would be very inaccurate, would require a bunch of manual intervention to try to test, evaluate, and modify it. Once we go through this step a few times, we will hopefully have something that is useful, and then we can start defining the causal effects that are of interest to us and we want to estimate. We call it identification, and if the effect is estimable, it's not always the case. The identification method can give us an estimation strategy, and then we can take this estimation strategy and use any of our estimators, such as linear regression for the simplest case, and do an effect estimate. So I'll go through each of these steps in a bit more detail. So starting with the causal discovery part. So the goal is that we have some data. We want to learn the causal graph from it. And if you look at methods, there are a bunch of automated algorithms to do this. But when you apply this in practice, most of them would fail miserably. So some of the problems these methods have, that they are very sensitive to the algorithm that we are choosing or the hyperparameters that we are using. So depending on the algorithm that you're using, you will get varied outputs. So it can be anything. The second problem is more theoretical, that multiple causal graphs can represent the same observed data. So we have no way to distinguish between those. And because this is an unsupervised learning problem, we don't have access to any ground causal truth. We have no way to check which of these learned models are correct or the best. To show some of these issues, I have a small example where this is adult income data set. This has been collected from the US Census, and this has a bunch of socioeconomic variables. And let's say our goal was to try to understand what factors directly affect the income of an adult. I also want to point out that this is a very difficult data set for causal discovery, so some of the results that I'll show is pretty bad, but it's not always just bad for all data sets. So for example, if we apply some of the most commonly used algorithms to this data set, so on top there's PC, and then there's hill climb search. You would notice two things, that both of the graphs that we have learned are missing quite a lot of edges that we would expect. So for example, on the top, we would have expected an edge from, let's say, education to income, or hours per week to income, but those are missing. Similarly, in the second bottom graph also, it has made some mistakes, like there's an edge from income to education, but it should definitely be the other way around, or same for hours per week. The second thing is that these two graphs are very different, so which is a more accurate graph. It's very difficult to tell. To further illustrate this problem, if we use the same algorithm, in this case PC in both these cases, and if we just change the hyperparameter, which is a conditional independence test here, you could see that you again see the same problem. They make mistakes, plus very different results. So, well, yeah, so the problem is that these algorithms make mistakes. So one possible way to fix this in a lot of cases is to somehow integrate expert knowledge to building these models. And this is something that we have implemented quite a bit in pgmpy. So it allows users to specify expert knowledge in a variety of ways. So for example, blacklisting edges or fixing some of the edges which we are confident in. Or specifying an initial graph, because some of these optimization algorithms, it can be quite helpful if we give them a good starting point. And something that we are also working on is to be able to provide temporal information, so time series information that what comes after something, so there's a direct causal link there. Just to show some example, like this is specifying blacklisted edges, so the algorithm doesn't consider those when constructing the graph. Then there's fixed edges, so we can make sure that those edges end up in the final graph, and providing an initial starting point for the optimization. So even with, so this seems like a lot of manual work, and even after specifying all that, we don't really always get to a correct graph. So this is something that we have been working on called expert in the loop. So this is supposed to simplify some of this expert knowledge integration stuff. So what this algorithm basically does is to rather ask the user for the expert knowledge in advance. It kind of iteratively asks information when it requires it. So this can greatly reduce the amount of manual information that the user needs to provide, as well as it asks questions about that then. And the other thing that we can do is that if we don't have an expert, we can just use an LLM. So how this works, basically, to show an example, is that so this would we would call the estimate method, and it would start building the network. And as soon as it requires information about the direction of any edge, it would prompt, and the user can specify this information. And it keeps on doing this till it finishes building. Or the other way around is that we, instead of providing the information manually, we give some description of these variables that the LLM can then use, and let the LLM decide some of these directions. And with that method, we are able to achieve pretty good results in a lot of the cases. And as you can see in the same example with this very difficult data set, we still are able to capture a lot of the relationships that we would expect. So that was the causal discovery part. So the gist is that it requires a lot of manual intervention, and you need to specify a lot of expert knowledge to build anything sensible. Even with that, most of the times we would end up with some mistakes in the model, and usually what we do is to try to test or evaluate those models that we're getting out of causal discovery. And the problem here is, again, that we don't know the ground truth information. So how do we do that? So we have collected a bunch of ad hoc methods that people have been using in research, and try to provide that. So for example, one of the methods is called testing for implied conditional independencies. So each of these DAG models implies a bunch of conditional independent statements, and then we can use these statements and run a statistical test on the data that we have. And if the test fails, that implies that our data does not match with the model that we have, and based on that, we can make some modification to our model. So pgmpy has a simple function, implied CIS, to find these independencies and then run these tests. So for example, the first row here is a test of relationship as independent of race given the other variables. And we get a very small p-value, and this implies that the independent statement does not hold in our data. So we would either make some modification in our model to fix this. So another metric that we have implemented is called Fisher's C-test. So it essentially combines a lot of these conditional independence tests into a single p-value. So this can give you like an overall fit of your model. So for example, in the example here, I've used the model that we had learned earlier. And as you can see that the model has a very small p-value, signifying a very bad fit. Whereas if we use like some simulated data, we can get a decent fit out of it. Another metric is correlation score. So this tries to figure out how much of the correlation that we are observing in our data is also explained by our model. And it is a F1 score-based metric. And this can be useful for comparing different models that we have built. So a higher score would imply that our model is better able to capture the correlations. Similarly, there's another one called structure score. This is based on the likelihood of observing our data given the model. Again, this can be used for comparing multiple models. So, and that was the DAG building process. So we either use an algorithm or manually build something. Then we go through this testing evaluation phase, and hopefully we have something that is seems correct. And then that could kind of be the end goal in some studies where, for example, we just wanted to understand how these variables are related to each other. Or, yeah. But if we wanted to then kind of also quantify how much of a causal strength is between some of these variables, we can go to identification and estimation step. So with identification, we basically try to see if the causal effect that we are interested in, is it even estimable given our model. And so in these two examples on the top, on the left, we have something called a confounding variable u, so which is unobserved in our data set. And on the right, we have the same model, but the confounding is observed. So on the left, the parameter, if we were interested in, was in between x and y, so the causal effect of x on y. It won't be identifiable in this model. There's no way to estimate it from observational data. But on the right-hand side, if that was observed, we can do that. And there's a theory behind it called do calculus, which can which provides a complete solution. So if there's a parameter that's estimable, the do calculus can give us a way to estimate it. The problem, however, is that there's no efficient algorithm to run do calculus. So what we usually do in practice is to try out a bunch of identification strategies that work in special cases. So just to show some of them. So for example, this is called the backdoor criterion, where we have a confounding variable which we try to control for. And there's a function pgmpy for that. And you can basically give this function the model, the DAG that we have, and x and y, the causal effect that we are interested in. And it would give out all the variables that we need to control for. And then we can use, based on that information, then we can define an estimator. For example, if we were using a linear regression, that would imply that we would run a regression equation, something like this. Similarly, there's a bunch of these identification criteria, and there are new ones always coming up. So another one is front door, very similar idea to backdoor, but it's a kind of a double application of backdoor, and it works in a specific case when we have mediator variables in between the causal effect that we are interested in. There's another one, instrumental variables. It's again a special case where Z here can act as an instrumental variable, allowing us to kind of estimate the parameter. So with identification, we basically get to an estimation strategy. For example, these equations here. So what basically you need to do to estimate these parameters. Then you can essentially use any of your favorite statistical models to actually estimate those parameters. And typically, people use linear models just for their interpretability. Some other features of pgmpy that I wanted to highlight were simulations. So because this parameterized DAGs are generative models, it can allow us to simulate data from it. And that can be helpful in a bunch of things. For example, just understanding these different causal concepts like confounding, bias. And another thing is that we have built pgmpy to be very extensible because this is a very active field of research. We have new methods coming in all the time. So for example, if you wanted to try out a new conditional independence test, you can simply write a function and you can plug it back into any of the causal discovery methods in pgmpy, and it should work. So in future, we plan to build some more practical methods like bootstrapping, better conditional independence tests, and adding a few more algorithms. I was trying to come up with a nice take-home message, but this is the best I could come up with. So causal inference is hard, but can give very valuable insights when done right. So thank you for listening.
Thank you. Yeah. Thank you, Ankur, for your nice presentation. So now, questions? And
hi, just curious about how does the package help deal with reverse causality, if it allows?
Reverse causality?
Yeah. So, for example, price influence quantity and vice versa?
So I think that's very, again, potential outcomes kind of framework. So, no. Yeah, so it's, again, so I think the main difference here is that this DAG framework does not have as robust estimators as compared to potential outcomes framework. So if your goal is to estimate a single causal effect, for example, as you mentioned, the reverse causality between something, you should most probably use potential outcomes framework. The problem usually there is that these methods usually assume that you know what your confounding variables are, what your collider variables are, which are very difficult to see from just your variables. So I think a combination of these, so for example, doing some kind of causal discovery to figure out these variables, and then utilizing that information to better estimate your potential outcome method, that could be a good approach.
thank you.
Hey, thank you very much for the talk. It's definitely trying it. My question is about the redundant variables. Like if you have highly correlated things, do this method automatically isolate them in cliques or that kind of stuff?
Actually, a lot of methods would fail in just that. But if you have highly correlated variables, I think a lot of methods would require you to actually remove those. It would just, because internally it would try to run conditional independence tests, and when it tries to do that, if you're doing like a linear regression kind of test, you would get a multicollinearity error, and it might just fail. So yeah, I think you would need to pre-process it out before putting it.
Yeah, got it. I expected it. So if I may, a short question regarding the colliders, because a lot of focus is also probably in your package on the confounders, but in my experience, interpreting colliders, it's even more difficult. Do you have some help on that?
Yeah, so that's one of the main reasons I prefer this DAG framework compared to potential outcomes framework, because here we don't have any difference between collider or confounder, right? Because once we start trying to learn this graph, we get everything out from this graph. We don't have to specifically define, okay, what we think is a collider or what we think is a confounder, but this graph is then our ground truth. Like, we accept it as our truth. Like, here's all the assumptions that we have made, and now we can do the estimation on that. So I think it's a bit helpful in that.
More questions?
Thank you. You said that we don't start with ground truth, so can two different researchers come up with two different DAGs, even with an expert in loop, and then does that change the process and they come up with different solutions?
That happens. There's actually a recent study which exactly did this, where they put a few researchers together and everyone came up with a different DAG. So it's we don't know which is the correct one. It's I think there are people who are working on trying to combine some of these methods. So like if someone came up with like 3 different DAGs and from experts, how do we combine these 3 into a single DAG on which then we can do estimation? Yeah, but I don't think there's a very good way to deal with it.
Thank you. Any more questions?
Hi, thank you for the talk. I have a much simpler question. I keep hearing that causal inference is very interesting, but it's a very niche thing, or you need to have some kind of special data, or at least a very large data set. Is there a good rule of thumb? Like, is your problem, like, can your problem actually benefit from causal inference, or you shouldn't even try it? Thanks.
I think in general is kind of the kind of question you're trying to ask. So I would come back to this, like if you are only interested in predicting, I don't think there's a need to do causal inference. But if you want to ask these questions, like what if I change something by something, so I think typically people take examples of, for example, if you're a supermarket, you wanted to see like what happens if I change the price of a product by X, what would be the effect on the sales? So it's a causal question in that sense. So in those kind of scenarios, I think you can try out causal methods.
I was wondering if the sort of the causal inference community for specific use cases do work towards something like benchmark data sets that somehow, at least for the specific problem, do give some guidance there, and if that maybe helps converge to DAGs that fit that specific use case really well?
Yeah, so I think there's some work on that. So there are some very, I would say, benchmark kind of models, like alarm or insurance. These are very commonly used models. But the problem usually there is that we are again, so both of these models are quite sparse, and that kind of biases towards methods which go for sparser models. So for example, the PC algorithm and hill climb that I showed, both of these are kind of biased towards sparse graphs. So, but if you look at fields like epidemiology, where the graphs are expected to be much more denser, and it just, so these, so there's no standard benchmark in that sense yet. I imagine someone will come up with it more like, more specialized towards specific use cases, like more specific use cases, I think.
Yeah, thanks for the great talk. I have a question to run this analysis. Is the sample size or number of observations is a problem and a limitation?
Is it a limitation?
Yeah, is it like if we have not so many observations, can we still derive the DAG diagrams or not?
I don't think there's a very clear answer to that at all. It would depend on a lot of things like your density that you're expecting from your graph, the number of variables that you have in your graph. So I don't think there's a very straightforward answer to that. Like it would be depends, but again, like more data is always better, kind of the general thing.
Any further questions? One last question, maybe? All right.
Yeah. Very interesting talk, so thank you. I was curious, so how do you choose between potential outcomes framework versus DAG process? Like, do you have like some sort of rule of thumb to go for one over the other?
Yes. Rule of thumb, if you just want to estimate a single causal effect that you're interested in, go for a potential outcomes framework. If you are planning to do more kind of causal discovery, you might want to check a few different estimates, do DAG framework. Or the best, I think, is when you combine both of them. When you start taking some of the information that you get from the DAG and apply it to potential outcomes, then I think you can combine both of them in some sense. Yeah.
All right. Thank you.
Yeah.
Thank you again, Ankur, for your presentation.
Thank you very much.
So thank you for joining the session. We'll have lunch at the ground floor, and we'll see you.